In this lesson, lesson 16 of cycle 3, we're going to revisit trigonometry. And since we're going to be doing a lot of work with equations of trig functions, it's in our best interest to make sure that we review a few things first that we've hopefully learned in either earlier in this course or else in previous courses. So let's just get to it. In the previous cycle, we saw that one complete revolution of a circle in radians is 2 pi. So you may still think of things in terms of degrees, and that's natural, but you want to remember that while 360 degrees is a full revolution of a circle in degrees, it's equivalent to 2 pi radians, and that's what we're going to work with in this course. We also learned how to convert between radians and degrees. We saw that pi radians is equal to 180 degrees. So that's the conversion factor we're always falling back on. And here's a couple of examples, radians to degrees. If I had pi over 4 radians and I wanted to change it to degrees, then I could multiply it by 180 degrees over pi. Pi's cancel out. 180 divided by 4 equals 45, and your answer's 45 degrees. Going the other way, if I had 45 degrees, then I could multiply it by, flip the fraction, pi over 180, and again, then I can just reduce. 45 goes into itself once and into 184 times, so I'm left with pi over 4. So you can go back and forth pretty easily. We can type things in our calculator. We can do it in radians. Sine of pi over 4. We have to make sure our calculators are set to radians. Mine is set to radians. I think in the bottom left-hand corner it says degrees, which would change it to degrees, but it's on radians now. So if I want to do the sine of pi divided by 4, for this calculator I have to do the fraction first, then I hit sine. I got 0.7071 to be exact. And then cosine of pi over 4. Also 0.7071. And then we were supposed to do tan. I might as well do that while I'm here. So tan, pi divided by 4, tan of that is 1. So that's pretty easy to remember. Cosine we had the same as for sine. And for tan it was equal to 1. So we can type radian calculations into our calculators, no problem, just like we could with degrees. We just have to make sure we're set to radians. Now remember, on a unit circle, we have angles in all 4 quadrants. We always start on the positive x-axis and measure this way. I'll erase that. But we're always going counterclockwise from the positive x-axis. And so if we think of it like we could go in an entire circle, then it makes sense that this line here would be the radius. But as you can also see, the radius is the same as the hypotenuse of the right triangle we form by connecting the point P to the x-axis. And as far as if this point P has got x and y coordinates of x and y, whatever they are, then obviously the distance between the origin and that point horizontally is just going to be x units. The distance vertically between the x-axis, the origin, and the point P is going to be y units. So we've got labels for the 3 sides of our triangle. And remember, r again is the hypotenuse. For the angle theta in here, x would be the adjacent side, and y would be the opposite side. Opposite to what? Opposite the angle theta. So the primary trig ratios, of course, are opposite over hypotenuse. So for sine, opposite over hypotenuse in this unit circle would be y over r. Y is our opposite side, hypotenuse is r. Cosine would be x over r. Tan would be y over x. And then for the reciprocal trig ratios, we just flip things upside down. So cosecant is the reciprocal of sine, so it's going to be r over y. And secant's the reciprocal of cosine, r over x. And tan, flipped, reciprocated, becomes cotangent, that's x over y. So when we have actual x and y values, numbers in for a particular point, we can then use those values, the x and y, we can calculate r using the Pythagorean theorem, since it's a right triangle, and we can come up with all the trig ratios that we need. Another thing that we need to review is special triangles. You would have done special triangles back in grade 11. Now, unfortunately, these triangles all look the same. I don't like them. I'm going to erase 2 of them because I think that they're misleading. In other words, I like the triangles to sort of look like the angles they represent. So one of the special triangles we saw before was the 30-degree triangle. This sort of looks like 30 degrees down here, doesn't it? However, 30 degrees, we're using radians now. So let's convert 30 degrees to radians by multiplying it by pi over 180. And what we'll see is that it goes into itself once, goes into that 6 times. So 30 degrees is the same as pi over 6. So I'm going to get rid of this. I'm going to actually write pi over 6 right in here, if I can get it small enough. That's pi over 6, same as 30 degrees. And in the same triangle, we could do the 60 degrees, because 30 and 60 always went together. 60 would have been up here, right? But we're not going to use 60. We're going to use radians. There's a couple ways we can come at it. We can just, again, multiply by pi over 180. And 60 goes into itself once and 180 3 times, and we get pi over 3. Or we know that 60 is twice as big as 30, so we could just double this. Pi over 6 times 2 would become 2 pi over 6, and that would reduce to pi over 3. So however you get at it, 60 degrees in radians is pi over 3. And you may remember the special triangle for the 60-30 triangle was 1, 2, root 3, like that. Sometimes you may have seen it drawn a slightly different way. Let's see, draw a nice triangle here. So I'll just redraw the 60-30. That looks kind of 60-30-ish, doesn't it? So here's the 60, pi over 3. Here's the 30, pi over 6. And then the sides went 1, 2, root 3 around like that. The other special triangle was the 45-degree one. And 45 degrees, we saw, is the same as, we saw it just above, 45 is the same as pi over 4. So we've got our pi over 4 triangle, which is 45 degrees, same as 45. And it went 1, 1, root 2. So in grade 11, you would have been shown where those numbers come from. I won't take up time with that right now, but these are our special triangles. And then we can combine those different sides, opposite, adjacent, hypotenuse, to come up with some values for some common angles of pi over 6, pi over 4, pi over 3, which are equivalent to, again, to 30, 45, and 60. Also, we had a cast rule. So the cast rule was something to remind us about what's positive in which quadrant. So cast rule went CAST like this. That was to remind us that all trig ratios are positive in quadrant 1. And in quadrant 2, just sine is positive, and cos and tan are negative. Let's put that in, how do I want to do this? Sine is positive, I'll put it in brackets here. Cos and tan are negative. These brackets are confusing. I don't like that. Let me get rid of the brackets. Cos tan, negative. We'll just leave it like that. Okay, in quadrant 3, tan is positive. And that means that sine and cos are negative. And in quadrant 4, cos is positive, and sine and tan are negative. So, cast reminds us of what's positive in what quadrant. That's all that that's about. Another thing that we need to review is related acute angles. We usually use beta to represent related acute angle. So that Greek letter that looks like a B, that's beta. And we use that, remember, we're always measuring angles to the x-axis. So if I want to have an angle of, say, 135 degrees, or in radians, 135 degrees would be 3 pi over 4. And what the angle we want, we usually call theta. We always measure it from the positive x-axis. But we can work with the related acute angle beta, which is just also measured always from the x-axis, but it's always less than 90 degrees or pi over 2 in radians. And being able to work with beta just helps us to work with the special triangles, and then we can put everything together and come up with answers to problems. Here's a pre-filled in version of the unit circle. So it's called a unit circle because we're talking about something that has a radius of 1 unit. It's got, for our purposes, I've got angles on there of in degrees and radians. The way we'd read this is, again, from the positive x-axis, from here to the first line would be 30 degrees, or pi over 6. From here to the second line would be the 45, or pi over 4, and so on. So we can just keep following, I can pick any line going from the positive x-axis to where I've drawn the arrow would be 135 degrees, or 3 pi over 4. So that's part of how the unit circle works, just reading that part. But then we also have the values that are around the outside. So if it's a unit circle, if it's got a radius of 1, remember this length from the origin to anywhere on the circle has got a radius of 1. So that means that we can, if we use our trig ratios that we just reviewed up above, anywhere there's an r, we can divide by 1. Notice how sine, that means, is just going to be equal to our y value, or y is going to equal sine, because on the unit circle, r is going to be 1. Cos is just going to be equal to our x value, because if the radius is 1, x divided by 1 is still just x. So x is going to be our cos. So that helps us find values on the unit circle. So what do I use? Green and blue. So that's just to remind us. So x is just going to be defined as cos theta. Sine y is just going to be defined as sine theta. And then we could use our special triangles. So for example, pi over 6. If I want to get the cosine of pi over 6 to get my x value, well, cosine of pi over 6 is going to be adjacent, root 3 over hypotenuse, so root 2, not root 2, just 2. So root 3 over 2, and lo and behold, that's what we got here. If you go back, I won't go back right now, but if you were to go back and do opposite over hypotenuse for a pi over 6 triangle, you would get 1/2. And that's what's going to happen all the way around the circle. That's where these different values are coming from. Notice how in quadrant 2 the x values are negative. right? Negative, negative, negative. No big surprise there because all x's are negative in quadrant 2. In quadrant 3, y and x are both negative, again, because quadrant 3 we're on the negative x-axis and the negative y-axis. Quadrant 4, just the y values are negative. And again, we have the cast rule around the outside here. That's what this stuff is telling us, just the cast rule. So just repeating it. Here's just another neater version of it. So I know that this first one's handwritten, and this is just a neater version which is generated on a computer, so you can take a look at that one if you like. It's showing the same thing. Here's some examples of things that we can do if we put all this information together. So use the unit circle to determine the exact values, and that's an important key word, exact values of the 6 trigonometric ratios. So sine, cos, tan, cosecant, secant, and cotangent for an angle of 3 pi over 4. So for sine, 3 pi over 4 is going to equal, from back up here, 3 pi over 4 was here. Oops, that was supposed to be a highlighter. Here, and we had sine would be negative root 2 over 2. Sorry, sine would be positive root 2 over 2. Cosine would be negative root 2 over 2. I just got my coordinates mixed up for a second there. So root 2 over 2, cos is negative root 2 over 2. Tan, you may remember the identity that says that tan theta equals sine theta over cos theta. So we could then figure out tan by doing sine 3 pi over 4 divided by cos 3 pi over 4, since 3 pi over 4 is theta. And then we know that that's equal to root 2 over 2 divided by negative root 2 over 2. If I want to divide fractions, I invert the bottom one and multiply. These cancel out, the root 2's. The 2's cancel out, but I still have that negative sign there. It all works out to equal negative 1. Okay. Cosecant is going to be the inverse of sine. So for the cosecant one, cosecant 3 pi over 4 is going to be 1 over sine 3 pi over 4, which is going to be 1 over root 2 over 2. Again, weird fractions in fractions, kind of ugly. It's the same as 1 times 2 over root 2, which is going to equal just root 2 over 2 over root 2. Now, it's ugly, it's bad form to leave a radical sign in the denominator. So I'm going to rationalize the denominator. I'm going to multiply the top and the bottom by root 2. When I do that, I'm going to get 2 root 2 on the top, and on the bottom, when I multiply root 2 times root 2, I'm just going to get 2. And then I can simplify this a bit. I know there's many steps, but my final answer I'm going to get is just root 2. So, cosecant started with this, ended over here as root 2. Maybe to save a little time, since secant is just the reciprocal of cosine, and we already saw that sine and cos were the same, except that cos was negative, I think we can assume that, and check it for yourself if you don't believe me, but if we go through all this work, if we start with everything the same, but it's just a negative value that we're starting with cosine, we're going to end up with a negative root 2 for secant. And finally, cotangent is the reciprocal of tangent, which means I'm going to take my value of negative 1, I'm going to do 1 over negative 1, which is just going to equal negative 1 as well. So these are my 6 values. Next question, does sine pi over 2 equal 1/2 of sine pi? It's a logical question to ask because maybe with math we can just rearrange it like that. But if we were to check sine pi over 2, pi over 2 is same as 90 degrees. Sine is just the y value, as you know, it's the 1 there. So sine pi over 2 equals 1. And sine pi is actually equal to 0. So it would be 1/2 times 0. If we go back to our unit circle, you can see that there's pi there, and the y value of that coordinate is 0, so sine pi is 0. 1/2 times 0 is 0. They're not the same. They're not equal. Okay, and last question, as a bit of a word problem. Ravinder is flying his kite at the end of a 50-meter string. The sun is directly overhead. The string makes an angle of pi over 6 with the ground. The sun being directly overhead means that we're going to get a vertical line. Wind speed increases. The kite flies higher until the string makes an angle of pi over 3 with the ground. How convenient. 2 special angles. Determine an exact expression for the horizontal distance that the shadow of the kite moves between the 2 positions. All right, well, let's draw our picture here. So it's pi over 6. So it's fairly low to the ground. And we've got, so pi over 6 is the angle, and the string is 50 meters, and we want to find the distance the shadow of the kite moves. So the shadow's on the ground, right? This is the shadow along here. Let's call that D1. So I could write, or I could find an expression for that. I can say cos of pi over 6 is equal to adjacent over hypotenuse, so D1 over 50. And then I could rearrange this a bit and isolate D1. Well, first of all, pi over 6, we've already seen is root 3 over 2. You can check the unit circle, though, if you want to confirm that. So D1 over 50. And if I want to isolate D1, then I can multiply both sides by 50, and I get 50 times root 3 over 2. I could reduce that. I could divide the top and the bottom by 2, and I'd get 25 times root 3. If I do the same thing for the other triangle, once the kite has flown higher, now we've got pi over 3 as our angle. You can see that the distance, the shadow's gotten shorter. The kite string's still 50 meters. Let's call this D2. Do the same steps. And cos of pi over 3 is just a half. Zoom in so it can be a bit neater. And so if I isolate D2, a half times 50 equals 25. So how much shorter has the kite string become? It's gone from a longer length of D1 to a shorter length of D2, so it's gone from 25 root 3 to just 25. If I want to give an exact expression, then I need to leave the radical sign there. So I could common factor out the 25, because there's two terms there, leave the root 3, and negative 25 divided by 25 is 1. There's our exact expression. Determine the distance in part A to the nearest meter. So, in other words, this is an exact expression. If I type this into a calculator, then I'll get a more rounded expression, but it'll make more sense as well. So I want 1/10 of a meter. So I could take the square root of 3 minus 1, multiply it times 25, and I got 18.3. So the distance is 18.3 meters. So we saw a variety of different things, and there's a lot of stuff in this lesson, so make sure you review all the different types of topics that we covered.